Hello students, today we are going to talk about diffraction. What is diffraction? It is rather a not clearly explained phenomena, but more or less we can say that it is a phenomena in which light bends about the obstruction, sharp edges of obstruction, and is able to reach the shaded area, the area shaded by the obstruction, and this causes formation of fringes having central bright fringe followed by alternate dark and bright fringes on either side with diminishing intensity and width. Well, in this we consider the same thing, that the two light waves are interfering, superimposed upon one another to form the fringes. But in this case, we have a different situation. The two secondary waves originating from a wavefront are superimposed, and they form the alternate fringes. So it is slightly different from the interference pattern and the calculations, all mathematical work we have done for interference, in which we saw that we considered two point sources and found the path difference between those two sources reaching any point P on the screen, and that was deciding whether that point will have bright fringe or dark fringe on the screen. But in this case, we don't have 2 point sources only. We have so many large number of point sources, because a wavefront, according to Huygens principle, is capable of generating secondary waves from all the points lying on the wavefront, and therefore we need to consider and tackle so many wavefronts generated from the single wavefront of light received from a monochromatic source. Here you see we have a monochromatic source of light which is allowed to pass through the lens, and then it passes through the slit area. Slit area is shown by the red mark, and the wavefront is named as AB. And that wavefront which emerged out of the slit is focused on the screen, and that at that place the condition for bright fringe and dark fringe is satisfied, and accordingly the color, the brightness or dark fringe or bright fringe is formed at that point P. Well, in case of diffraction, we have two type of diffraction. One is Fraunhofer's diffraction, and another is Reynolds diffraction. In case of Fraunhofer diffraction, the source as well as the screen both lie at infinite distance from the slit, and that case is depicted in this picture. You see, we have a monochromatic source of light, and that is placed in such a way that the light emerging out of the lens becomes parallel, and so effectively parallel ray appears to be coming from infinity. So the source of light is at infinity from the obstruction, from the slit, and also the wavefront emerging out of this slit area is again a plane wavefront, that means parallel ray. So that also effectively acts as if it is reaching some infinite place, and so it is a Fraunhofer type diffraction. In case of Reynolds diffraction, we have the slit at finite distance from the source or the screen. So we are not talking about Reynolds diffraction. In this case, in case whenever we allow a monochromatic beam of light to pass through a slit, we get a pattern of central bright fringe that is called central maxima, and that is followed by alternate dark band and bright fringe, dark fringe and bright fringe on either side of the central maxima. What we shall be doing is we shall be taking the different case and dealing with it in a different way. But in case of interference, we were able to tackle in single way the condition of formation of bright and dark fringe. But in this case, we don't have this liberty, because we have more than two wavefronts emerging out of the wavefront AB, and they are interfering at this point. So we take the different fringe and deal with differently. In case of the central bright fringe, what you see, all the rays reaching from point A to O1 and reaching from point B to O1, they have zero phase difference, and that satisfies the condition for bright fringe. And we can have in similar fashion another two mirror points. Means if we have equidistant from the center, 2 points equidistant from the center O, then the ray reaching O1 from those two equidistant points will again have zero phase difference, and therefore we will in all cases the condition for bright fringe is satisfied. So all the rays reaching point O1 from this wavefront AB are having constructive interference. That means central bright fringe is formed at center O1. Now if we deal the first minima, which is enveloping the central maxima, we deal it in a different way. For the first minima, we take the wavefront into two equal parts, say AO and OB. Now what happens? We consider that the ray reaching point, any point P we have considered, that the ray reaching point P from A and from O are having phase difference of lambda, and therefore phase difference of lambda by 2, and therefore the total phase difference between the ray reaching point P from A and from point B reaching point P will be lambda. Means lambda by 2 is the path difference for point A and O, and another lambda by 2 path difference is for another group O and B, and that means the total path difference between rays reaching P from A and B is lambda. Now what happens? We consider several similar points equidistant at a distance of A by 2. AB length is taken as A, and half of that distance, the distance between point A and O, is A by 2, and if we shift by some distance, say L, from A towards O, and by same distance we shift from O towards B by same distance L, then we have two corresponding points both lying at same distance A by 2, And since we have taken that the path difference between the rays reaching point P from A and O, that is separated by A by 2, is lambda by 2, so any other point will have the same phase difference lambda by 2 reaching point P, and therefore we can write the path difference between point AO, that is lambda by 2, therefore path difference between point AB written by delta AB, that is A sin theta 1, is equal to 2 into lambda by 2, that is lambda. And since the path difference between the rays reaching from AO and that reaching from OB both are in opposite phase, so they cancel each other, and therefore dark band is formed at point P if if A sin theta 1 is equal to lambda. And for that reason we can also write sin theta 1 equal to lambda by A. This relation we can also write sin theta 1 equal to lambda by A. Well, this is the condition for first minima, and let us call it equation number 1. Now we talk about the first maxima, means the minima is followed by another maxima, and to explain the formation of bright fringe due to first secondary maxima, we divide the whole wavefront AB into three equal parts, and we take the path difference due to each part equal to lambda by 2, and as a consequence the path difference between point AB will be 3 times the path difference between 1/3 part, that is AP1 we have named, so therefore path difference between AB is 3 lambda by 2, and therefore we have for AB we write A sin theta equal to 3 lambda by 2, and therefore we can have sin theta 1 equal to 3 lambda by 2a. Therefore we can have sin theta 1 equal to 3 lambda by 2a. Let us call it equation number 2. Well, the screen is quite congested because we were having so many things to be mentioned and the space was not that much, so I am very sorry for that. Now we talk about the formation of secondary minima. That means the bright first secondary minima will be followed by second secondary minima. First secondary maxima will be followed by second secondary minima, and to deal with it we divide the whole wavefront AB into 4 equal parts and proceed in the same phenomena as we have done while dealing with the first minima. We were having 2 equal parts, now we are having 4 equal parts, and from the each part the path difference was taken to be equal to lambda by 2. We have named it at RC. So therefore the path difference between point A and B will be 4 times the lambda by 2. That means A sin theta 2 equal to 2 lambda. That means sin theta 2 equal to 2 lambda by A. Let us call it equation number 3. And as we have done, we have dealt the first secondary maxima, we shall be dealing with the second secondary maxima, and so on and so forth. We divide the wavefront AB in 5 equal parts and take the path difference for each part to be equal to lambda by 2. Therefore, path difference between AB will be equal to 5 times lambda by 2, and therefore A sin theta 2 is equal to 5 lambda by 2. Therefore, we can write sin theta 2 equal to 5 lambda by 2a. Let us call it equation number 4. So we have tried to explain that how the central maxima, the first maxima and first minima, second maxima and second minima are formed, and how it could be explained, because we have so many points on the same wavefront releasing secondary wavelets, and so they how they interfere to produce the bright fringe or dark fringe at any point. It would be very difficult if we deal with all the individual wavefronts, sources of secondary wavelets originating from the main wavefront AB, and therefore we have adopted this method. I believe that you have understood to a great extent. Well, it is very tricky, I understand it, and for that reason I will request you to repeat this lecture, listen it very carefully, everything, every time you see, if you consider bright fringe, you will have one factor left unnullified, and that is responsible for producing the bright fringe. But in case of minima, no unpaired part is there to survive, and therefore it produces minima. That's all for today. Next day we shall be finding the fringe width for diffraction pattern. That's all for today. Thank you and have a nice day.